as you said, I would also like it if it's more like a discussion.
Yeah.
Yeah, it can be very interactive, and when you have a question, directly tell me. And yeah, so I'm now presenting our joint work about NOMU. It's abbreviation for neural optimization based model uncertainty. So we want to study model uncertainty, and it's two of the other first authors, Jakob and Hannah. I think maybe Jakob joins later, but Hannah is also here, so I've already seen. And okay, so I directly start with the question, what is model uncertainty? Very basic. So at the moment, our algorithm only works for regression, not for classification. We think we can probably also extend it to classification, but we are mainly interested in regression. And so here, for a very simple case, if you have a one-dimensional input and a one-dimensional output, can you see my mouse when I? Yeah. There is an unknown ground truth function that we don't know, but we just observe a few data points from this function. And even in the noiseless case, because we don't know the ground truth function, in between the data points and outside when we extrapolate, there's still uncertainty, epistemic uncertainty. And so we can fit the neural network to make a prediction, but this usually is just one-point prediction. So we are also interested in epistemic uncertainty or model uncertainty. And yeah, our algorithm that I will introduce today, at the end, we will see how it's able to make this epistemic uncertainty bounds. So probably most of you know other algorithms like deep ensembles or Monte Carlo dropout, which also estimate model uncertainty. But we think many of them have some problems. For example, when we fit Monte Carlo dropout, so we abbreviated with MCDO, Monte Carlo dropout, what we see is that it's kind of doing almost the opposite in this example of what we would intuitively think what good uncertainty bounds should do. Because here from good uncertainty bounds, what we would estimate if we know that there's no noise, so we tell the algorithm there's no noise. At an observed training data point, we know already what's happening, there's no uncertainty, but only if you move further away from what you have observed, there should be more uncertainty. But here for Monte Carlo dropout, we see that it's not doing this here where you have a lot of data points, there's a lot of uncertainty, and here in the biggest gap where there's no training data, we have the smallest uncertainty. So this is has a problem. And in theory, for Monte Carlo dropout, you can prove that under some very theoretical assumptions, it's approximation of a Bayesian neural network. And a Bayesian neural network, so for every reasonable Bayesian method, it should not look like this. And in the original paper where they showed a plot where it looks nicer than trained for 1 million epochs, then it would also look a bit similar to this. But if here we trained it for 1,000 or 4,000 epochs or something, and it still has this strange shape. And I think
one question, can I have a question about this? So is this result robust, like to the I don't know, dropout probability or the model capacity, like i.e. the size of the model? Because I could imagine if the noise is small enough or the model is large enough, then the model should learn to filter out the noise perfectly on these data points.
so. Okay, what do you mean filter out the noise perfectly, or
like when you add dropout, it's like multiplicative noise on the activations, right?
Yeah.
And if the model capacity is large enough, then it should be able to filter out this noise. Like given the noise is not too large and the model has enough capacity to filter it out.
So then what it should converge to also for very wide networks, it should, if you perfectly optimize it, so with this probabilistic loss that you make kind of infinite many gradient steps, then it should optimize to something which is deterministic at the training data point, so that it always achieves zero loss. But it would vary in the gaps in between the.
Right.
So that's the theory, but in practice, so here we used a very large neural network,
Mm.
which should be really possible to at the data point always do the right thing. But just with a couple of thousand epochs, it's not enough. We would
Okay.
need more 1,000,000 epochs to get this. But we have not tried every different sizes. So I mean, it would be. So my feeling is that also for other sizes it would not be better, or that
Yeah.
is quite a general problem. But it could be that there's some yeah. But we in all our experiments we always observe this problem for Monte Carlo dropout.
Okay. Thank you.
And I think in many benchmarks, you have a mixture of epistemic uncertainty and aleatoric uncertainty. So there you don't really see this problem so much because maybe if you have noisy data, it's not such a bad, for the overall uncertainty, it's not so far off that you don't directly see that it's really bad. But here in our experiments, we always focus on the noiseless case. And there you can more obviously see what are the problems of Monte Carlo dropout. Okay, yeah, I also have some backup slides to explain more difference between aleatoric and epistemic uncertainty, but I think most of you know the difference. Okay. Okay, so and now also for other methods like Gaussian processes, often they don't really look exactly how our intuition would tell us how they should look like. And for Monte Carlo dropout, like in theory, it's this. I mean, in theory, these Bayesian methods are very nice, mathematically defined, but in practice, both the implementation and even if we argue, even if we theoretically could approximate some Bayesian neural networks posterior perfectly, it's not clear if they're really good because it's not clear what the good prior is. And I think it's often very hard to have the right intuition what is a good prior. But actually, what you can see in this picture is that we all have quite a clear intuition how the posterior bounds should look approximately. And so what we do is quite unconventional. So usually people first try to come up with a prior, and then when to approximate the posterior, because they think they have more intuition on the prior. But we question this and say maybe if we actually have more intuition directly how a good posterior bounds should look like, we make an algorithm who gets us posterior bounds that fit to our intuition. So we try to write down our intuition for this, how model uncertainty bounds should look like. We write the desiderata for this. So our first desiderata is that it should never be negative, the uncertainty. So the uncertainty is the width of the uncertainty bounds. I think this is quite trivial and boring. Then the second one, so I mean, the only method that I know that could violate this would be quanta regression. So it's for aleatoric uncertainty, not epistemic uncertainty. For the quanta regression, this could happen. But yeah, usually this is not a problem. Okay, then the second one also sounds very obvious that if you have noiseless data at the training data points, there's no uncertainty left. But as we see in practice, many methods like MC dropout, they struggle already with this basic desiderata. Then the third one is the larger we move away from the training data, the more the uncertainty increases. And then the fourth one is a bit more complicated. I will explain it in more detail in the next slide. And then what's interesting about the fourth one, that Gaussian processes do not fulfill them. Okay, and the fifth one is then a very intuitive one again, that if we, as the limit of data goes to infinity, then the epistemic uncertainty vanishes at the support of so if the distribution covers everything, then we will have everywhere infinitely many data, and then there should be no epistemic uncertainty left. Okay.
I would have one question. So do you have an example? So you mentioned for D1 and D4, some models that do not satisfy this desiderata. Do you have some examples for the other desiderata of some models?
So I think reasonable for D3, for example. So okay, for D2 I gave the example like MC Dropout does not. So in theory it should fulfill it, but in practice does not fulfill it. For D3 here in theory MC Dropout should fulfill it, but in practice it does not fulfill it. Here in the largest gap you have the smallest uncertainty, and very close to the data point you have the largest. So that does not fulfill. And also all the methods that estimate aleatoric uncertainty, they have no reason to fulfill D2 and D3. They also do not. If you so aleatoric uncertainty, you just estimate the noise scale, and the noise scale, there's no reason to believe that the noise should be larger far away from the observed training data than close to the observed training data. But every reasonable method to study epistemic uncertainty should, especially in the noiseless case, it should fulfill D2 and D3. But as we see, even methods to estimate epistemic uncertainty, such as MC Dropout, in practice, it does not fulfill it. And yeah, D4 Gaussian process does not fulfill it. And D5, yeah, also methods that estimate epistemic uncertainty, they should fulfill it, but methods that just estimate aleatoric uncertainty. So an example for measuring aleatoric uncertainty is if you just give a second output to the network architecture, which learns the sigma, and then in the loss, you take the log likelihood of a Gaussian with mu and sigma that you estimate the to just estimate the noise scale. The noise scale, if there's a noise not equal to 0, then it would also not go to 0 in the data to infinity. Okay.
Is D5 a relaxed version of D2, or does it mean for every?
Yeah, you can see that that if D2, if it's not if you only have a countable number of training data points, then there will always only be a null set of points where you actually observe something. But if it's kind of dense, then also if it's just surrounded by infinitely many other things that are very close, then it should also go to 0 uncertainty. But yeah, it's related. So it's kind of D5 is something like D2 plus continuity is.
Okay. And like D4 implies also something like calibrated uncertainty, right? So that
okay, then
yeah,
I would not really say so. Okay, I think I see how you interpret it, but it's not how I want to formulate it. In the next slide, I will explain D4 more detailed. But in general, we only look at relative uncertainty. So this is orthogonal to calibration. So for every uncertainty, here we always have this scaling factor. And calibration we only do by the scaling factor. And when we compare different methods, we also compare against deep ensemble, hyper deep ensemble, Gaussian process, all these methods. There, the goal of the method is only to calculate the relative uncertainty, like where is it larger and where is it smaller compared to each other. So here it should be larger than here, and how much we scale it to calibrate it. This we all use the same calibration for. We use the same calibration for all of the methods, and this is not part of our contribution how we calibrate them. Okay, but for D4, maybe I should. Are there more questions to calibration, or because for D4, I think go to the next slide and we.
No, it's fine. Thank you.
Yeah. Okay, more focus on D4. I start to explain a Gaussian process which does not have D4. But you could also see in the previous slide, all other desiderata they do not depend on the Y labels at all. They only depend on the X positions of the data. And D4 is the only one which depends on the Y label. And here for a Gaussian process, if you calculate, so here there's a different plot now. Here we have X1 and X2 axis, and the color represents the uncertainty. So yellow means high uncertainty and dark purple means almost zero uncertainty. And here these white dots on this regular grid are the training data points that we observe. And here I do not plot the Y label, I only plot the X positions of the training data points. And for a Gaussian process regression, if you look at the formula for Gaussian process regression, the uncertainty does not depend at all on the Y values. It only depends on the X values. So, and if we have some symmetric isotropic kernel, like radial basis kernel we used to generate this plot, because the data points are on this regular grid, then the uncertainty has certain symmetries here. And yeah, so it always looks like this, no matter what values you take for the Y labels. And for this specific instance, we took, for example, that the Y values on the right-hand side, or these 8 Y values, they all have as a label, as a target, as a Y value, that's always +1. And for those 8 points, it's -1. And what we expect from a reasonable uncertainty method, for example, our algorithm fulfills it, that the algorithm learns that X1 is an important feature to predict the data points, because this decides if it's +1 or -1, and X2 is completely irrelevant. It does not have any, on the observed training data points, it does not have any influence. So then the uncertainty, if you go from a point a little bit at the training data point, there should be 0 uncertainty, and if you move a little bit away in this unimportant X2 direction, the uncertainty should stay lower than if you move away in this important X1 direction, because X1 is more important. It should grow more in the X1 direction. And so it should also grow a little bit in this, but more in this direction. Later we will see how you can control how much you want this, because there's also this effect of feature collapse. In our language, this would be too much D4, that if it would not grow at all, the uncertainty in this direction, this is something you also typically don't want, because only on this final training data set, it looks like X2 is completely irrelevant, but you don't know for sure if it's completely irrelevant. And yeah, NOMU can also, here it's just simple features directly X1 and X2, but NOMU can also learn more complicated nonlinear features of the data. And yeah, I think this is one of the most important aspects of deep learning, that you are able to learn these features, because if you look at the human, for example, how they perceive uncertainty, if you learn some properties of some images, for example, then if there is we would directly think of what are important features and what are not. And if one picture is exactly the same as one of the training pictures, but maybe just the background was removed by another background on a Euclidean distance, this would be a very, very different image, because all the background changed. So you should be theoretically very uncertain about it. But in practice, we see that the background is not such an important feature. So we should learn that we don't need to be that uncertain if the important features stay the same and only an unimportant feature moves away. And as I said, that the Gaussian process is not able to do this. From this, you can imply that also neural tangent kernel or infinitely wide Gaussian Bayesian neural networks are also not able to benefit from this D4, because the theory says that neural tangent kernel, it's again just a Gaussian process, just with a specific kernel, and for infinitely wide Bayesian neural networks, it's also infinitely wide Gaussian Bayesian neural networks, it's also a Gaussian process with a specific kernel, so they are not able to benefit from the desiderata D4.
But you don't know the kernel, right? For an infinitely wide model.
Yeah, I don't know
Maybe
the kernel, but this statement is independent of the kernel, so it won't look exactly like this, but it will always be, for example, it always has to have this symmetries, because no matter what the kernel is, we know that it's for neural tangent kernel and wide Bayesian neural network, it's one fixed kernel, so we can prove that the uncertainty does not depend on the Y labels. So in this example, for example, we don't know exactly how it looks, but we know that it has to have the symmetries. That here it's the same as here, so it cannot look like this because this breaks the symmetry between here and here.
Okay. So I don't know how the math works behind it, but like, so for example, if I would train let's say an ensemble with infinitely many members, then I would expect the result to break the symmetries.
Yes, but if that's also in the neural tangent kernel paper, they use a very specific setting where they have some very weird scalings that you don't use in practice.
Mm.
And what the neural tangent kernel proof, if you would train an infinite ensemble of infinite wide neural networks with this strange neural tangent kernel scaling, then it would be symmetric. This follows from the theory, because from the theory it follows that it's a Gaussian process with fixed kernel, and then you can say this. But
so in this instance, but for me to understand it, so in this instance means that if I use this specific scaling plus infinitely wide neural network, then it would converge to something that is symmetric with respect to the origin. In this, okay.
Yeah, and so
but that means that this infinitely wide neural network could not learn any function, right? Not every function, right? Because
it can learn every function, but it cannot learn interesting features. So in a Gaussian process, this is only the uncertainty. The mean prediction can fit through the data, but only the uncertainty will always be symmetric for this grid.
Okay.
Yeah.
All right. Thank you.
Yeah. Okay. So this like finite neural networks, or if you also infinite wide neural network with a reasonable scaling that are not covered by theory so well, because neural tangent kernel only works for the strange scaling, then you have this feature learning, this desiderata D4, but you lose it with this theoretical neural networks here. And yeah, for example, there's also a paper that postulated that the neural tangent kernel posterior, this is the perfect form of uncertainty, and they tried to compare the performance of uncertainty methods just by comparing them, how close are they to the neural tangent kernel posterior. And I think this is a very bad idea, because it's, in my perspective, it's obviously not the perfect uncertainty model, because a perfect uncertainty model should have some feature learning, some D4, and because for this neural tangent kernel, in some situations you have some closed formula which makes it tempting to use it, but it's it does not have D4. Yeah. Okay, but yeah, and then some other theory Hannah and me are working on that. If you have L2 regularized networks, also in the width to infinity, you always have feature learning, and this is also then the reason why our NOMU algorithm is able to have this D4. Okay, and just another example where you can see D4 also that here in this region where nothing, that they're all equidistant, the points, but here in this region where nothing really important happens, the uncertainty is smaller, and here where more happens, the uncertainty is larger. Just another example. Okay, so how does our algorithm work? So we also have two outputs, one for the mean prediction, one for the uncertainty, as this is the same as for this very basic algorithms that just learn aleatoric uncertainty. But the difference is for us, this should learn epistemic uncertainty. So we need a very different loss function. Okay, so the loss function is for the mean prediction, it should fit for the data. So there we just take a standard squared loss. And then the epistemic uncertainty sigma hat f, we want it to be at the training data points close to 0. So we here also make it close to 0, or only if it's 0, this loss is 0. Okay, and now the important part comes, that here this is a continuous loss over all of the input range, where it everywhere pushes up the uncertainty a bit. And so in practice, we simulate this with this continuous integral with a Monte Carlo approximation, that in every batch we sample new random input points that push up the uncertainty. And so the training data points in every epoch, we have the same training data points that are always strongly pushed to 0. And everywhere in between, we have this soft force pushing up the uncertainty bound.
How do you choose the points for?
They are randomly sampled, and at the moment we just use a uniform distribution on the input range. So we make some cube around the data, and with I think something like 10% around the data, and uniformly sampling them. But we think for some more complicated data sets like images or something, this is maybe a weird distribution. We should maybe just take some unlabeled set of images or something like this. But yeah, at the moment on tabular data, we just use uniform random points.
So also for in-distribution data then, or?
Yeah, it's for example, in this example, it would be uniformly from a little bit to the left of -1 to a little bit to the right of +1, something like 10%, or maybe 5% on each side or something, or a 10% average. But we make this loss here much stronger, that it pulls it to 0 at these data points, and this is really a discrete real force at this training data points, and this because it's an integral at every single position, it's infinitely small. It only accumulates over wider ranges.
But then how does it fulfill D4?
Okay, I come in a second, maybe before, but I just should say, if you would only take this loss as it's written here now, then the solution would be that at the training data points, the uncertainty is 0, and in between the training data points, the uncertainty is everywhere infinite. But because you have implicit or explicit regularization or both, it cannot learn these jumps to infinity, but it rather makes these smooth bubbles here. Okay, and now how do we control D4? Here for D4, so we have here a main architecture. This could be anything, fully connected, convolutional, transformer, anything. And then we take the same architecture here, but with independent weights. And here we make these connections, and these dotted lines mean that in this direction there are only forward passes but no backward passes. And so here it is, and we use, on all weights, we use a little bit of L2 regularization. So, and here the network is more motivated for the sigma hat F to use those features that it needs already for this task, instead of learning its own features. But what we can control by how we make the ratio of the regularization of those weights and those weights, we can control between feature collapse. So if you would make here the regularization infinite large and here small, then we would have very strong D4, but it would be some feature collapse. That then we only use the features here that were powerful to learn just normal prediction task. And other features would be in other direction, there would be no uncertainty at all. And if we make the uncertainty, if you make the regularization equal here for both networks, there would be very, very small D4. So it would be almost no D4. It would learn something almost as if the no D4, there's just a little bit more uncertainty in this direction, because then it can save some regularization costs here if it uses the features that are already, it needs anyway for this task. And so you can continuously control how much D4 you have, depending on how you make the trade-off between these regularizations. And yeah, and we also experiment a little bit, but this is not, we didn't do enough experiments in this direction, but that if we also make maybe connections from other hidden layers here, to have in different levels of abstraction, there could everywhere be some uncertainty. Okay. Yeah, so then here these are the most important hyperparameters, and there, as I said, the ratio between the two regularization here and here is also an important hyperparameter. Yeah, so the uncertainty bound that we use for the upper uncertainty bound, we use then the mean prediction plus the learned uncertainty scaled with a factor C, and for lower bound with a minus here.
I have one
Hi,
question.
sorry.
Yep.
Oh, sorry. So please go first. Yeah.
Okay, sure. So with respect, so regarding this term, this loss term with the integral, so if the input is unbounded, then you cannot choose like a uniform distribution, right? Because
So if it's bounded, we can use a uniform. Or you mean if it's unbounded, or what?
yes.
Okay. Yeah, if it's
and-
unbounded, then what we do that for the training data that we observe, they are always in some bounded range. So what we do in practice, that we fit the cube around the training data points, and then add in every direction 10%. I'm not sure, 5%, 10%, something like this. I think this is probably not optimal, but it kind of works already. And what you should also think about that, if you would plot this wider, the neural networks. So in some other paper, we have some theory what's the inductive bias of neural networks, and our result can be summarized as something like it likes to have low second derivative, low curvature. So if we would continue this drawing here, then it would, maybe I can even use a pen here. Then the uncertainty would continue something like this, even if there are no further of these artificial points that make the uncertainty larger. Just because of the inductive bias, if it sees a trend here, it will continue this trend, and the uncertainty will always increase if you go further here, without the need of having more of this without the need of extending this integral outside of this range.
But is that true in practice? So when you try on many different tasks, I feel that it might not be counted all the time, right?
That what is not always?
So I mean, the fact that if you go outside of this cube where you suffer from a training time, then it could be that if you're unlucky, I guess this might happen in some direction, that then the uncertainty will not grow as expected, but maybe, I don't know,
Yeah,
just collapse and be very low. So I was wondering also with respect to this other desiderata D2, I think it
yeah,
was.
it's especially in higher dimensions. This we think that this is becoming a problem in some cases, that we don't have enough of these data points, that we are unlucky, and in some regions we don't have one of these artificial data points where we should have one. Yeah.
Makes sense.
So yeah, the actual application we had in mind when we developed it, they had usually something like 20-dimensional or something like this, and there it's still okay, but it's maybe starting already becoming a little bit of a problem. But for really high-dimensional things, this could be a more serious problem, that we don't everywhere have these artificial data points where we want them. But I mean, in total, we sample really a lot of them, because in every batch we sample something like 200, 500 new random data points. And yeah, we train it for many, many epochs, so we have seen a lot of these random points during training.
Okay, makes sense.
Yeah. So,
Hey, sorry for that. What about the assumption 5, the D5, so which requires the sigma f to be 0. So if we were arbitrarily far away from our data set X, right? So how to guarantee this assumption
And
here?
D5, so this is only in the limit infinitely many training data points. And so this we have proven that in that because of this term gets stronger and stronger the more training data you have. And so if you have infinitely many training data points in the surrounding of every point X, you have a lot of training data points. And so it's okay, but so the limit is not uniformly. So for every point X, maybe if it's a point X that is very far away, maybe we need very, very many training data points until also around this point there are enough training data points. And if in a small environment there are enough training data points, then this term dominates over this term. Because here we do not divide by the number of training data points.
Yeah, I see.
Yeah, so there in our paper we have a proof that if the number of training data point goes infinity, it actually fulfills this D5.
Yeah, I see. Thanks.
Okay. Then we tested it on some regression data set. First here we have a generic test bed where we can generate as many true functions as we want to make it statistically significant. And there to have there are not so many noiseless data sets. And here we can control the noise because we sample our true functions ourselves, and we sample them from a Bayesian neural network. So we take a network with random weights to get some true functions. And yeah, here, at least in 1 to 5D, it's NOMU significantly better than the other benchmarks, including MC dropout. And according to the theory in the MC dropout paper, this would be because we sample exactly from this PNN prior the true functions. So the best thing what you mathematically possibly could do is to make the posterior uncertainty bounds for exactly this PNN prior. an MC dropout claims to approximate exactly this posterior, so it should be unbeatable for this specific benchmark. But because in practice it doesn't work so well, even after we train it, I think more than 1,000 epochs, we are significantly better with our strange little method, which is intuitive based and not theory based. And yeah, then this is a Gaussian process with some radial basis, kernel, and deep ensemble and hyper deep ensemble. For hyper deep ensemble, also the hyperparameters differ among the ensemble members. Yeah, then, okay, our method is only for noiseless data sets, but we wanted to try how much it hurts us if we use a noisy data set, such as the UCI regression data set. And then it's, yeah, for some data sets we are better, for some not so much. It's not really made for noise, but it's still I would say on par with the other methods. Yeah. Okay, then very briefly, aleatoric versus epistemic uncertainty. So the brown one, it just learns the aleatoric uncertainty. And here, because we have noiseless, it's always approximately 0. And so that you can even see it, we blow it up by factor times 5. But this is just very boring uncertainty, which is everywhere the same, and it does not have this effect that we want. But the application that we at the start had in mind is Bayesian optimization. So for Bayesian optimization, we are not interested in learning the function everywhere. At the end, we are only interested to find the point x where the function achieves the maximum. And for Bayesian optimization, the uncertainty is very helpful, because I mean the naive approach is that we just start with some random points, then fit the neural network through, and then check where is this prediction the highest, and then to decide where we sample the next point, we take the point where the prediction is the highest. But this would get stuck at this point if we are constrained to -1, 1. Here for the prediction, this is the highest point, and we would keep sampling or querying always this point and learn nothing new. And okay, the idea of Bayesian optimization is that every time we ask for the f of x for a given x, this is very costly to ask this question. But at the end, we want to have a good approximation of this. And what you can see here for these methods that don't fulfill this desiderata D2, that the uncertainty goes to 0 at the training data points, such as here this very wrong method that just makes aleatoric uncertainty, not epistemic uncertainty. So I mean, it's a good method for aleatoric uncertainty, but it does not make sense to use it for epistemic uncertainty. Or something like Monte Carlo dropout looks a bit similar. The problem that we would get here is that even so, the idea of Bayesian optimization is that we use the upper uncertainty bound as acquisition function. So then this means that the next query we make based on where the upper uncertainty bound is the highest. And if we would use aleatoric uncertainty, we would always, it would give kind of the same uncertainty bonus to every point. So we would still always get stuck in this and always keep querying here. And then for epistemic uncertainty, what you can do is maybe here it would, okay, here it's close, but maybe it would again, even if you look at the upper uncertainty bound within -1, 1, here this point would be the highest. But then, as we said, this is only relative uncertainty, and calibration is not so much our focus, because especially in Bayesian optimization, if it would suggest as the acquisition function optimization, we should query again at here this point. We know that we have queried this point already, or we can have some epsilon tolerance if we query the similar point already. And then we can instead of querying here again, we can tell our algorithm that it should be more curious to explore something new, that we just scale up the uncertainty by a bigger factor. And if you would scale up by a bigger factor, because here the uncertainty is the largest, if you scale up the uncertainty by a bigger factor, then some point over here would be the next suggestion that we can query. But for aleatoric uncertainty, even if we scale this up by a factor of 1,000,000 or something, if it's everywhere the same, even if we scale it up by a factor of 1,000,000, it's everywhere the same, so we would get stuck here. But yeah, we don't get stuck if we have a reasonable epistemic uncertainty, which has this D2 that at the training data points it's 0. So even if we scale it up, it's almost 0 at the training data points, but on other points, it gives some additional motivation to also query there. So then we, here, okay, this is just on the left is the detailed setup, how our Bayesian optimization thing looked like, but then here, we also again compared against many other methods, and here we have again strong results for our method up to 20-dimensional settings. Okay, yeah, I think the time is already a bit late, so yeah, thank you for your attention, and yeah, if you still have questions, you can ask. Yeah.
Yes, yeah, thanks so much for the presentation. So maybe I would have one question that you quickly mentioned in the beginning is, so this focuses on regression, but for classification, how would you extend this method?
Yeah, I think it's for classification like, some additional complications that for classification it's a bit harder to make a difference between epistemic and aleatoric uncertainty. So for so you don't have this mean prediction and the uncertainty, but you have at the end you always have this class probabilities. And so what would be so at the moment it's also only for noiseless things. So noiseless classification would mean that we a priori know already that for every input it's deterministically always belongs to one class. So there are no inputs, for example, no images where you say maybe 50% would classify it as a dog and 50% would classify it as a cat. So like a picture where there's a dog and a cat. This would be already some form of aleatoric uncertainty if the same picture would be labeled differently by different people. Yeah, but there are some also in classification some situations where it's always for each input clearly that it belongs to one class. And in this situation, yeah, we think we could extend it to this things, yeah, but we have not really tried yet. But
why is it exactly a problem if there is aleatoric uncertainty?
Okay, so okay, there would be also some okay, there would be also some things how we can some tricks how we can kind of include aleatoric uncertainty, but it's a bit dirty or because so and if there's aleatoric uncertainty, also if you want to estimate the epistemic uncertainty, so desiderata D2 is not fulfilled anymore. Even at the training data point, there should be some epistemic uncertainty because we only had noisy observations of this point. And then, so what kind of fixes this problem is if you make this mu square a bit softer or less strong, so that also at the training data points, the uncertainty does not go completely to 0.
Okay, so then you would try to model aleatoric and epistemic uncertainty with your sigma f, right?
No, we could also try to separate it. Okay, so here, so for aleatoric and epistemic uncertainty, you have it's still so if for here in this noisy setting here, there are directly credible intervals for f that their job is it's their job to capture f with a high probability, and then there are predictive intervals for the y given x. So so the red one captures epistemic plus aleatoric, and the blue one only epistemic. But already for the epistemic, so we could estimate aleatoric uncertainty somehow with a third output that estimates aleatoric uncertainty. So this is not so much of a problem, or we assume that constant aleatoric uncertainty is something. But even the epistemic uncertainty, if you have noisy data, it should not go to 0 at the training data points. Because if you only have a finite amount of training data points at this exposition of only one training data point, we don't know exactly what the true function is because we only had a noisy observation.
Ah, so if the observation is noisy, yeah.
Yeah, if the observation set value is noisy, then yeah, we also have epistemic uncertainty at the training data points, and this, I mean, this could be, if we make the mu square very weak, then we would have some uncertainty, also epistemic uncertainty at the training data points. So this
but then you would assume that, or then you would define noise on your input data as epistemic uncertainty, or
no, we could still separate this by a third output that only learns the aleatoric, and this sigma still only learning the epistemic uncertainty, but then there is aleatoric induced epistemic uncertainty. So a noise-induced epistemic uncertainty. It's because we had noisy observations.
So you basically mean, okay, so I have noisy observations, so I'm a tiny little delta away from my actual real training, my real data.
Yeah.
So I should be already in a regime where I have, if the data was noiseless, where I had some epistemic uncertainty.
Yeah, or the epistemic, or mathematically, I would for the for me the epistemic uncertainty, it's always this. It's the distribution of f of the true f given the train. So if you imagine that the data comes from such a process that you have the true f, which is unknown, but once if you would know it, it would be deterministic, and plus the noise, and the noise every time you observe it, it's a new noise.
But that's not input noise, right? I mean, that's label noise.
Oh, sorry, it's label noise, yeah. Okay, I did not talk about input noise, sorry, that was a confusion. But this would be additional level of, this would be additional source of uncertainty, yeah. But even if you only have label noise, you have already also that the epistemic uncertainty is not 0 at the training data point.
Oh, I would say so, actually.
Yeah.
I mean, like, so for example, if I would train a Monte Carlo dropout model in the correct way, then it would go to 0 at that point, like even if I had some aleatoric uncertainty or an ensemble.
No, because you don't know the true f at this point if you only had a noisy observation.
Okay, so if the observation was noisy, okay.
Yeah, if the observations that you've seen, if they were noisy, I think if you have noise, then usually also the observation in your training set have noise. Or I mean, maybe there's some situations where you. But what?
Then it's getting very philosophical, right? Because, like, okay, I have some data and that's noisy.
Yeah.
And then like, okay, do I want that my epistemic uncertainty on the noisy data has some value larger than 0? Because I know that there was some real non-noisy version of the data that I actually wanted to fit. Or do I say, okay, look, this is just the data that I have, and I accept that my epistemic uncertainty would be 0 here, and I just hope that my aleatoric uncertainty method is picking up this additional entropy in my conditional distribution. I don't know.
Yeah, I think mathematically, if you believe like in this model that there is some true function f, but you never observe it, you only observe these noisy observations of it, then the distribution of the true f also at this point x, you still have some uncertainty there because you don't know what the true f is. You only know once you observed for this x, you observed this y value. But if you would observe for the same x another y value tomorrow, maybe it could be different. And okay, it will be different because of the noise, but also you don't know the mean of this conditional distribution for sure. Because maybe when you yesterday observed it, the noise was positive, so you have so then the actual mean is lower than what you observed in this observation. And if you would observe it 100 further times, the mean would always be below what you've observed.
Okay.
Yeah.
Okay. Maybe one last question from my side, at least. Sorry, we are already over time, but that was burning on my tongue. So, do you have some ideas, or are you already working on scale, like what you do when you scale it to really large dimensions, like some efficient sampling techniques, or?
Yeah, so I think then it would be good to have some unlabeled data set that we can use for these random points to approximate this integral, that we don't waste them on some completely nonsense regions, but have them only if we believe in some manifold theory that the reasonable data lies close to some small dimensional manifold, maybe that we use some unlabeled, but we have not tried this. And I think I think there are so many methods for uncertainty, so we don't need to be the best for everything. But I think it's the strength here is more for low dimensional. But we at the moment worked together with Jakob. We made a paper where we use it in a very specific economic setting, and there it works very well. And there it is noiseless and low dimensional and regression. So I think it's mainly. I mean, we know already that it's strong in some very specific settings, but yeah, I mean, it would be interesting to try out other settings, but at the moment, I have not really. Oh, Hannah, you want to say?
Yeah, if I remember correctly, in the Bayesian optimization experiments, we sometimes tried in high dimensions to sample augmented data points for these integrals, predominantly around observed data points. But I don't remember if the outcome was better than.
Okay.
Yeah. I
yeah.
don't remember.
But this would also be an option, like in form of a Gaussian distribution around observed data points.
Yeah.
Just to pull up the uncertainty there a bit, and then let the implicit regularization of the network architecture work in between.
Yeah, because once you have this trend that it moves up, then it keeps moving up in this direction until there's something telling to do different. So
yeah, I remember there was also this work around Odin. I think I'm not sure whether it was in Odin. Like this is some algorithm that uses out of distribution data to push up some uncertainty. I think they mostly work on classification. And I think they used either adversarial samples or a discriminator. They also did uniform sampling, but I think it was tricky because they mostly worked on images.
Yeah, I think for images, it's probably not the best approach because it's so high dimensional and probably actually only on a low dimensional manifold or close to a low dimensional manifold. So, yeah.
Okay, cool. Yeah, thank you. Are there any more questions? Otherwise, yeah, thank you, Jakob, for the really, really nice presentation. It was super interesting. I really enjoyed it. And yes, I always love how Bertrand uses the Zoom emojis. All right. Yeah, thanks a lot for the talk. And I hope to see you around. And with this, enjoy, guys. Have a good evening.
Yeah, thank you for the discussions on this.
Thanks a lot.
You too.
Bye.
Bye.
Bye, everyone.
Bye.
Bye-bye.